Welcome to the course on power quality, and today we will cover this multipulse converters which are used for power quality improvement on AC mains, because these are AC-DC converters. Coming to the outline of presentation, we will like to discuss with the introduction, challenges in AC-DC converters, then we will talk about multipulse AC-DC converter, and we will discuss about advantage and application of multipulse AC-DC converter, then classification of AC-DC multipulse AC-DC converter, analysis of multipulse converters with the diodes and thyristor rectifiers, then an analysis of isolated fork connected transformer based AC-DC converter. We will talk about analysis of T connected isolated transformer based AC-DC converter, and then of course challenges in AC-DC converters are the major problems. AC-DC converters are injection of harmonics at the input and output, and harmonics cause dielectric, thermal and voltage stress, which cause premature aging of electrical insulation, and voltage distortion at the point of common coupling take place due to the voltage drop of harmonic current flowing through the system impedances. Well, it cause the capacitor bank overloading due to the system resonance, interference on telephone and communication lines due to noise induced from the power conductors, and it causes poor power factor, and the equipment damage from voltage spike created high frequency resonance resulting from notching. Well, coming to this multipulse converters, the multipulse converters define as diode or thyristor converters where the pulse numbers is more than 6, and generally the pulse number is a multiple of 6 assuming 3 phase systems. So, 12, 18, 24 pulse circuits are possible. A 12 pulse converter, for example, consists of two 6 pulse converter fed from 6 phase supply and connected in series or parallel on DC side, like 18 pulse have a 3 6 pulse circuits and so on. Well, this is typically the kind of table where we have a number of pulses in the converter, like a 6, 12, 18, 24 in normally used converter. Some people call it also conventional converter, and harmonics in input AC mains current, where K can be your positive integer like 1, 2, 3, 4, and then the ripple in output DC source. So, this will be like typically for 6 pulse converter you will have a harmonic 6 K plus minus 1. For example, 6 pulse you will have a 5th and 7th, and next will be your corresponding to 2 will be 11, 13, similarly your 17, 19 for 6 pulse, but 12 pulse you will have a like a 11, 13. So, all below 11 will be eliminated because of the your 12 pulse converter, and on DC side you will have a 12th harmonics of supply, and 18 pulse it will be like 18 plus minus 1. So, lowest will be 17 and then 19, and then next band of 35, 37. Similarly, 24 pulse it will be 24 plus minus 1, that is a 23 will be the minimum. All harmonics below 23 will be eliminated to 23, 25th, then second band will be certainly around 48, that will be 47 and 49. So, you will eliminate automatically many harmonics typically in this. And another important aspect, the harmonics which are present, they are also fundamental divided by that particular order of harmonics, and on the DC side you will have a ripple frequency corresponding to these number of pulses like. So, that the concept in, you can call it conventional or classical converter. We will talk about of course the converter which are not multiple of the 6 also, maybe in the next lecture. So, coming to the advantage of multipulse AC-DC converter, the performance parameters such as total harmonic distortion of AC mains current and ripple factor of output voltage improved simultaneously, and the improvement is independent of the supply frequency variation, unlike the passive filter, and minimal or no control required as diodes or thyristors are mainly used. They are economic, maintenance free and efficient, and phase shifting transformer are used to divide multiple phase supply from the 3 phase AC main using different combination of transformer winding, 3 phase transformer winding, because supply is 3 phase like star, delta, zigzag, 4, polygon, etc. And the application potential of them is like typically we divide of course into different category, like we talk about non isolated and controlled rectifier, AC-DC converter. So, they are used in front end of switch mode power converter like switch mode power supply, UPS, AC-DC motor drive, DC servos. They also use like a typically like aircraft variable speed constant frequency generation system and aircraft maintenance system using 460 and 400 Hertz converter system. Then another category will where we require of course the isolation. So, we have a isolated uncontrolled rectifier which are used like the railway working on DC and the welding equipment working on high frequency, and non-isolated control converter they are used like a DC motor drive system with regenerative capability, and some power supplies of large rating also use non-isolated dual converter. And of course, isolated control rectifier they are used like in HVDC, battery energy storage system, adjustable speed synchronous motor drive for of large power rating for applications such as mining, and then arc furnaces. Well, some of the typical examples you can see like AC motor drive of very large rating order of up to 75 megawatt, and then high frequency welding machine for initially for AC to DC conversion. Then HVDC, I mean HVDC system it has gone to even with the thyristor converter up to 6 gigawatt HVDC line. So, each converter station is order of that power rating like a 6 gigawatt means 6000 megawatt order up to that, but of course, lower power is also there like. Then arc furnaces for 3 phase which convert AC to DC, then later on you can use the DC for these furnaces, and this is the typical example of power supply for DC arc furnace. So, you have a typical example if you look into here we have a the converter with the transformer isolation, having a 24 pulse converter, and this is with the control, because even with the 24 pulse converter we are using the thyristor, it requires reactive power as well as the harmonics are also there. So, for that we use the normally passive filter. For reactive power of course, we use the thyristor control reactor, the reactive power leading is given by passive filter, and then of course, we have a control loop corresponding to like a electrode current like a DC current from here as well as from reactive power from AC side current. So, that control of arc furnace is done for which is reasonably high power like also. Well, the another is power supply for welding. So, we use the 3 phase supply for high power, normally use rectifier, then the smoothing capacitor for getting a regulated DC, then we use the inverter for converting into high frequency, and then we use the rectifier and filter, and then we have arc load typically for. Then configuration for multipulse AC-DC converter. Normally, we in this conventional AC-DC converter which have from 3 phase supply, we have a required phase shift is 60 divided by number of 6 pulse converter. Like you have a 12 pulse, so you require 2 converter. So, number of converter will be 2. So, 60 by 2 that will be 30 degree phase shift. If you require 18 pulse, there are 3 converters. So, 60 by 3 you will require 20 degree phase shift. If you have a like a 24 pulse converter which require 4 converters, so it will be 60 by 4 like a 15 degree phase shift among the different converters, or you have a typically like a 36 pulse converter. So, you have 6 converter. So, 60 by 60 you will require 6 typically the 10 degree phase shift like. So, like that of course, the large number of pulses are also used, like typically if we talk about Navy examples, at least minimum of 36 pulse converter required, because they can't afford more than 3% TAD in the typically on input AC mains current. So, number of converters also require reasonably large like. So, that is the one concept of phase shift. There are 3 concepts are used in this. One we use like a phase shift, another multi-phase, and third we use it like a phase, typically a pulse multiplication like. So, this is related to like if you talk about like a 6 pulse from 3 phase to 3 phase with transformer isolation. So, we have a 1 converter and you will get this kind of Cauchy square wave. Well, you do not have a triplen because of the 3 phase in that. So, triplen are not there. So, lowest will be 5th and 7th, then the second band will be 11th, 13th. But the important part is there because of the your stepped waveform closer to square wave. Whatever harmonics are there, they are of magnitude fundamental divided by that order of harmonics. So, if 5th is there, that will be 1/5 of the fundamental current, 7th will be 1/7 like. So, that is in case of this multipulse, there are some harmonics are eliminated and remaining harmonics are also reduced. That is the advantage of this multipulse converter. Now, coming to 12 pulse converter which require 30 degree phase shift between the 2 converter. When you have an isolated version, you can have a many connection for this 12 pulse. but here we are talking about plus minus 15 with the symmetric with using such kind of a extended delta connection. This we call it extended delta configuration, and you can connect secondary either in series or parallel, but if you connect them series, if application allow the sufficient voltage, then the current balancing automatically are there in that case. But the phase shift between two converter require the 30 degree because 60 by 2, and here 30 degree we are getting by plus and minus. So, here we are getting 15 degree, you can call it the leading compared to the input voltage, and here we are getting 15 degree lagging with respect to the input voltage because of the extended delta. So, number of turns accordingly from geometrical relation we calculate to get a phase shift, but you can have still the equal voltage, that their voltage will be on the same circle like. Well, if you have a 12 pulse, you will have this kind of the waveform, and in this waveform certainly it is a stepped waveform. Lowest than 11th harmonics will not be there, they will cancel out, and lowest will be 11, 12, it will be input current will have a 12 n plus minus 1 or 12 k plus minus 1. The lowest will be 11th, and 11th harmonics will be also 1 upon 11 of the fundamental. So, you can say that some harmonics are eliminated, but remaining are also harmonics are also reduced. That is the major benefit of this your multipulse converter like. And typically if we talk about the little analysis of this waveform, these are the magnitude for different degrees. Okay. If you talk about 30, 32, 60, 60 to 90 degree, and remaining 4 quadrant, 4 portion, remaining 90 to 180, and then remaining another half cycle are identical in magnitude, and you can calculate the coefficient of Fourier series from there, and then you can have a final expression from this. So, you will find fundamental is order of this in terms of the DC link current, and then third is not there, then fifth is also 0, seventh is also 0, ninth is also 0, 11th will be there, and that will be 11th will be the fundamental divided by h, means that will be like 11 here. Similarly, your 13th also will be like this. So, you will find harmonics which are there, lowest will be 11, 13 order of this much, that is 20 per typically 0.2 into ID, and this will be like even further reduced. So, so you can typically find out what will be the RMS current corresponding to taking a dominant harmonics. So, that will be the RMS current corresponding to 12th pulse converter, and this is your fundamental RMS here, and you can find out from the same waveform the typically fundamental, and then you can have even the Fourier from analysis the expression for different harmonics, like you can call it fundamental, then 11, 13, then will be 23rd, 25th in that, and you can find out the THD from this for this 12 pulse converter, and where it is. So, you will find it is a 15% THD in that case here. Like a 6 pulse, you will have a 30% around, and here you are typically you will require you will have a 15% in case of 12 pulse. This is without considering the leakage reactance, but of course, leakage reactance also responsible for reducing further harmonics on input AC, means of course, you have to you get little penalty for output voltage reduction because of the overlap or so. So, this is like 18 pulse. So, 18 pulse you will require phase shift of order of like a 60 by 3. So, you will require 20 degree phase shift, and you can see here this is the original in phase input output, but this will be 20 degree, you can call it like kind of leading, and this will be 20 degree lagging. So, and all three if you connect them in series, so you will have a symmetrical, let us say the same current in all. So, the primary current also you can calculate here, which will be sum of all the 3 currents with the phase shift, and you will find this kind of a waveform here. In this waveform, you will not have a less than 17th harmonic, because it is 18 n plus minus 1, and so lowest will be 17. So, below 17 no harmonics. So, 17, 19, and next band will be 35, 37. So, remaining will eliminate, all other harmonics will be eliminated, and the 17th harmonic will be 1 upon 17. So, that magnitude also will go on reducing, and 19th will be 1/19 like. So, that is the benefit further, that you are going to closer to the sine wave, the input current waveform or so. And then in 24 pulse, that is 60 by 4, means you will have a phase shift of 15 degree. So, you can clearly see here we are having plus minus 17, this is 15 degree, from here to here minus 7.5 to minus 22.5, that is also 15 degree, and similarly plus 7.5 to 22.5 degree, that is also 15 degree. So, you will have a 4 converter, and there may be many ways. This is what we use the extended delta configuration here for the secondary, so that the all secondary are identical and primary having a delta, but you can have a many connection configuration which we will discuss it. Because 3-phase transformer can be connected in many ways. So, we will like to indirectly discuss about that how many ways we can connect the 3-phase transformer windings, and which will be responsible for giving this kind of the phase shift which require different number of pulses converter like. And you can understand in 24 pulse you will get this waveform very close to sine wave, and in this waveform you will find the lowest harmonics will be 24 plus minus 1. So, 23rd will be lowest, and then next will be 25th, and then second band will be like a 47, 49. And you can understand here typically the even a 23rd harmonics will be 1 upon 23rd like. So, whatever harmonics, I mean majority of harmonics are eliminated, but which are there they also reduce, I mean slowly I mean like, and waveform goes closer to sine wave. So, coming to now 30 pulse, I mean it requires the 5 converter as you can see it, and 60 by 5 will be the phase shift. So, 60 by 5 like you have a 12 degree, and you can clearly see here we have a 0 degree, then 12 degree leading, 24 degree leading, so 12 12, and similarly plus 20 and minus plus 24. So, all have a 12 degree phase shift from one to another and third like. And here also we are using extended delta, I mean like for all the other winding except the main winding, and current is same because you are connecting in series. So, then analysis become quite simplified. So, in 30th pulse you will have a lowest harmonics to 30 plus minus 1. So, it will be 29th will be the lowest, and the 31 will be the next harmonics, and that 29th will be 1 upon 29, I mean of fundamental like. So, you will find that, I mean as we are increasing the number of pulses, the waveform is going more closer to sine wave, we are able to eliminate the harmonics, and in diode rectifier we do not have a reactive power burden at all like. Then we go for 36 pulse, you require in 36 pulse 6 converter as you can see here. So, the phase shift requires 60 by number of converter, so 60 by 6. So, you will have a 10 degree. So, clearly you can see here plus minus 5, that is 10 degree, then 5 to minus 15 10 degree, minus 15 25 10 degree, and similarly on the other side plus 5 to plus 15 10 degree, and plus 15 to 25 again 10 degree like. So, you will have a that 36 pulse converter, you can see the waveform exactly going to be very close to sine wave, and this you can consider here typically like the lowest harmonics here will be 36 plus minus 1. So, lowest will be 35 and next will be 37, and that next will be like your 71 73, I mean that is a 36 into 2 plus minus 1. So, 30 lowest for 35 means the magnitude of this will be fundamental current divided by the 35. So, you will be able to reduce this harmonics even less than typically even at 3%. I mean in this 36 pulse converter the lowest harmonic itself, and you will find the TAD will go on reducing like, I mean even the TAD will come less than 3% overall TAD, and that is the reason of course the transformer leakage reactance further will reduce the harmonics in this case. And normally it is considered for the Navy, whether Indian Navy or US Navy, they say that less than 36 pulse converter cannot qualify, they require total harmonic distortion and input supply current less than 3% with reasonably improved power quality like. I mean of course, because of diode rectifier we do not have reactive power burden. And then we have a like a 46 pulse converter, it has a your 7 converter, I mean of 6 pulse, and 60 by 7, I mean you will require a phase shift of typically 8.57 degree, and you can see here, I mean all 7 0 to plus 8.57, then 17.14, then 25.71. Similarly, on other side you have a minus 8.57, then minus 17.14, and then minus 25.71, and you will get the certainly lowest harmonics here will be 42 plus minus 1. So, 41 and 43 will be the lowest harmonics, and your waveform will be closer to sine wave of this input supply line current like or so. So, lowest will be 41, and that will be your fundamental current divided by 41. So, you will find this even less than 2.5% will be the dominant harmonics in that case. The next is the 48 pulse converter. I mean 48 pulse converter means you are using like 8 converter of the 6 pulse, and 8 converter by 60 by 8, you will find the phase shift here typically of 7.5 degree, and you can see here 3.75 3.75. So, that is a 7.5, from this to this it will be again 7.5. So, all converter consecutive converter will have 7.5 degree, and all transformer secondary also identical with extended delta to provide this much of phase shift from the original phasor like. And you will get a current typically very close to sine wave with this number of stepped waveform, and the lowest harmonic will be 48 n plus minus 1. So, lowest harmonic is 47. So, and that will be fundamental current divided by 47. So, you will get the TAD even quite low or not more than even 2.5% order of that like. Then we have a typically the complete spectrum here of all these conventional starting from 6 volt, 12, 18, 24, 30 and 36, 42, 48. Of course, we can go a high number of pulses, but you can call it the winding of the transformers as well as typically I mean like the number of converters go on increasing, but you can see the how the TAD is reducing from 31 to 15 point something, then 10, 7.5, then 6 and 5, then 4, but initially you will find drastic reduction, but after that you will find it is not causing that much reduction. But one thing you will observe 6 to 12 and 12 to 24 this will further half and half, and 24 to 48 further half. So, there is a typical relation like 12, 6 to 12 half of this, and from 15 to 24 further half, and from 24 to 48 you will find further half I mean like also. But of course, because of the even if we talk about like with the proper adjustment of leakage reactance in place of 10, people are able to report order of 2% less than 2% TAD even in 18 pulse converter like I mean also. Similarly, you will find the ripple filter or the percentage peak to peak ripple. I mean you will be able to see from 14 it came to 3.4 12 pulse, and then for 18 it is 1.6, and it gone from 14% less than 1% in 24 pulse converter. So, that is the reason like in many applications we are able to go like a depending upon I mean up to what extent we can afford the standard, and we go for typically different number of pulses like for different applications like according to the cost constraints and simplicity also in applications like. So, this is a comparative level for all you can call it 6 to 48 pulse converter, 6 pulse. These are the little benchmark because that is why we call it these are the multiple of 6, and they consider as a typically benchmark, and we call it conventional AC multipulse AC DC converter like. For remaining of course, we are able to design with the power some innovation we are able to get much lesser than TAD even lower number of pulses like. So, now coming to the classification of this multipulse AC DC converter, we normally these are 3 phase supply 3 phase, and why you can I mean like we are able to convert 3 phase supply either for phase shift with the help of transformer, or you can have a multi phase also, or you can have a mix of the both in these multipulse converter. So, we divide into unidirectional and bidirectional. Unidirectional use the diodes and bidirectional use the thyristor. Earlier in some application we were using the thyristor, but thyristor certainly because of the we require output voltage control, but it requires certainly the reactive power burden. Harmonics go on reducing with the higher number of pulses, but reactive power burden is there. So, in many applications which are unidirectional power flow like process industry like your electroplating plant, electromining plant, people are replacing the diode thyristor with the diode and then using the single IGBT for even up to 3 kiloampere or 5 kiloampere order of that, like they are available now. I mean with the not it does not require for DC control for very high frequency order of 3 kilohertz is reasonably well like I mean. So, there are plenty lot of changes. The benefit is that you are not having reactive power burden and you are able to reduce the supply current drastically down. Harmonics are eliminated by multipulse converter. So, if we divide this unidirectional, we can have a application requirement of isolation, or we can have a non isolated if voltage difference is not much different. Similarly, in your even a control one with the thyristor, and of course, thyristor technology go on pushing certainly for very high power rating. I mean like typically I told you LCI or HVDC kind of application which are going several megawatt, hundreds of megawatt order of that. But further classification of this is full wave and bridge. I do not know whether you could have gone through, we will discuss this what is full wave bridge and full wave bridge and full wave bridge. The full wave converter require the number of phases of supply equal to number of pulses. So, it means if you want full wave of like 12 pulse, then you must have to convert 3 phase supply into 12 phase supply and use the typically only the 12 devices, but the benefit is these are used considering for very low voltage high current application like electroplating, electromining, where even the losses in single diode will be substantial. So, you do not prefer the bridge circuit there, you prefer full wave circuit. We will discuss what are the kind of circuit for this full wave. So, broadly here we classified into 8 category, but day by day this unidirectional or diode rectifier or diode based multipulse AC-DC converter are getting popular for many applications. As I told you, like medium voltage drive of several megawatt, as well as many even typically applications where we want to convert AC into simple DC also. But power quality improved on input side as well as output side. Input side we reduce the total harmonic distortion and no reactive power burden. Output side we really have a very low voltage ripple or peak to peak ripple or ripple factor is reduced for the DC. So, we not only improving the power quality on input AC mains, but we are also improving the power quality on your output DC side of these converters like. Now, coming to first category of multipulse AC DC converter for unidirectional power flow, I mean like we classified like considering unidirectional multipulse full wave AC DC converter, and they are, I mean many applications we prefer to have them isolated unidirectional full wave DC DC converter, because I told you if we want to have a DC very low voltage and very high current, the voltage order of like typically 24 volt or 48 volt, but we want a current per kilo ampere. You might have seen the electroplating plant where we do the coating with the very high current is required, but voltage is very low, even the you can touch, person can touch because they are isolated and not too much voltage or so. So, these are possible with different transformer connection, and the kind of transformer connection we normally prefer to use here, we use that in full wave you require virtually a kind of a return path and all the transformer connection which can provide you a kind of facility of neutral, I mean for return path of rectifier, we prefer that. So, one is the star, another is the zigzag connection, then another is a T connection, and another of course is a Scott connection, which are not much different than T connection. So, these are the only connection which we can think about of using for typically primary we can use of any other connection also, but secondary we require certainly the neutral point. Like typical example, here is a 6 pulse converter, we are using primary delta and secondary we are using double star, which convert 3 phase supply into 6 phase supply, and because it is a 6 pulse converter. So, each phase, I mean you have a for each pulse you require a 1, let us say 1 phase for 1 pulse, and you have a same number of devices like. So, here the current which is flowing into the load, it is coming only through one diode. So, one diode losses are reduced, but when we are working at very low voltage, I mean typical example it may be 12 volt, the drop of one diode itself may make a losses corresponding to 3 to 4%, even more than that, I mean for very high current and very low voltage application. Even if you consider the diode drop 0.7 volt, and 0.7 volt compared to 12 volt is not less than even a 4% or 5% losses in one additional diode if you take a bridge configuration. So, where we require like a very, you can call it losses are very important, especially low voltage and high current application we prefer here. We use the interface transformer, so that this half bridge and this half bridge you can call it, they work simultaneously to have current like. It is not, otherwise if you do not have interface, then certainly out of 6 only one diode will conduct, but here you can have a conduction one diode from this half bridge, another from this half bridge, a set of, and that we call it like a 6 pulse converter like. So, this is what we call it the kind of full wave. So, number of pulses equal to number of devices equal to number of phases of the supply, which we convert 3 phase to into 6 phase in that case. So, that is why we call it isolated 6 pulse full wave AC DC converter employing delta to double star transformer. So, with the double star we are converting from 3 phase to 6 phase like. Now, coming to this another connection, I mean from delta to zigzag connection, I mean you can have a like a zigzag also, which convert again 3 phase to 6 phase. I mean the 6 phase supplies means 60 degree angle between adjacent 2 phases, and this is also another way of getting 6 pulse using zigzag. That was really with the star, this is with the zigzag, and this is with the T connection. I mean you can see the T connection here, primary is also T connected with the 3 phase balance, and secondary is also T connection to get like a typically 6 phases of 2 set T connections. I mean here, so you get a 6 phase supply and you can have a 6 diodes connected here of full wave, and you are able to get 6 pulse voltage across the typically across the load like. So, that is the connections like, and then of course, you can go for 12 pulse. So, 3 phase uniaxial 12 pulse full wave AC DC converter using isolated 2 transformer. So, what we do here, we have a 2 transformer, one is delta to double star and second is delta to star to double star, and they will have a 30 degree phase shift in all these 12 phases. So, one phase to another phase it will be typically like you have a, but you will require certainly interphase transformer here, I mean typically here to here, so that your conduction of all devices are there simultaneously. Typically from each group of 3 diodes you are having conduction of 1. So, simultaneously 4 diodes are conducting at the moment because of this interphase, you can call it the transformer, and here also you have interphase typically of the transformer like or interphase inductors like. So, we are converting 3 phase supply into the typically 12 phase supply, and we require 12 diodes for creating the 12 pulses in the output voltage which are applied across the load. Similarly, the concept here also, as we discussed in conventional one, that if you go to the 12 pulse, you will have a lowest harmonic 11, 12 n plus minus 1, so lowest will be 11. So, as we increase the number of pulses, we go on reducing the harmonics like also. So, now you can go with the zigzag connection corresponding to this, like you have a 12 pulse connection, that was with the typically you can call it with the star, and this is with the zigzag secondary, and 12 pulse, you have again you are converting 3 phase supply with the help of zigzag connection into 12 phase and using 12 devices to create the 12 pulse in the output voltage. And then you can have a even the T connection for 12 pulse, how you really design with the proper geometry as the circle voltage. These all 3 points of supply or all 12 point of supply should be on the same circle, so that you are able to get same RMS voltage at the output corresponding to the neutral point from primary side as well as from the typically on secondary side. Neutral here normally might have gone through is called typical connection that you have a neutral somewhere else, but we do not need the neutral because if you have a 3 phase supply, but secondary we need the neutral to connect the load here. So, from this neutral point or center point, if you take all the vertices like all they will be equal, and you will have a what we call it the 12 phase supply here. Then similarly, this is another connection for polygon for 12 pulse, and then you have a typically 18 pulse using the your star connection. So, we need here of course, the 3 primary, 3 sets of the transformer, and from this 3 phase supply of input we are converting 18 phase, and 18 phase means you are getting 360 by 18. So, you are getting a phase shift corresponding to here 20 degree from one phase to another consecutively, or you are able to use the 18 phase supply for 18 pulse converter with the 18 diodes, and here you will get 18 pulse in the output. Of course, in the input also you will get the harmonic order of like 18 plus minus 1, 17th will be the lowest harmonic. So, that will improve the power quality on input as well as the number of increased pulses in the output like. And then this is your typically a connection corresponding to 18 pulse with the another configuration to create like 18 pulse with the star, and then another your fork connection typically for delta to star. There are many ways to make the 18 pulse full wave, and only by using this we are able to have either you use the fork connection or you use the your reach connection of star connection or star with fork connection for providing the phase shift which you require for 18 phase 20 degree phase shift between neighboring the two and then the zigzag versus star. So, again we are able to get 18 pulse from this also, or we are able to get like a 24 pulse. This 24 pulse converter it was patented in 1948 in US and used for a very large number of applications. So, what we are converting here, this 3 phase supply we are converting to 24 phases. 24 phases means typically you can think about how much degree we require it, 360 by 24. So, you require like a 15 degree from one phase to the another phase of consecutive valve. First phase if you take it, it will be like a 15 to 30, then 45, 60. So, that is the 4 phase, and second phase will repeat, third phase will repeat kind of things like in that manner. So, you are getting 24 phase supply AC supply, and you are using 24 diodes for having a 24 pulse converter. 24 pulses will be in the output voltage which are across the load, and here also in the input harmonics also will be 24 plus minus 1 in lowest one, and you will have a 23rd, 25th. Second band will be again 24 into 2 plus minus 1. So, that will be 49, 47 and 49th harmonics. So, all other harmonic will be eliminated similar to like multipulse we already discussed. So, these are the kind of full wave concept like. Then you have a 24 pulse of order of your zigzag connection, and we have a star delta, and then you have a zigzag connection to convert 3 phase supply into 24 phase supply, and then we are using 24 diodes to create the 24 pulses in the typically voltage across the load. So, you can call it ripple in the output voltage as well as ripple factor go on reducing as far as the TAD in the input current also will go on reducing. Normally, we are not able to go more than 24 pulse for all these high power applications also, because it gives the quite good TAD less than because lowest harmonics is 23rd and you will automatically will get less than 5% TAD, and because of the effect of leakage further you can have a harmonics never the go more than 5%. So, you are able to qualify IEEE 519 standard, and that is the reason we consider 24 pulse reasonably. Otherwise, you will be increasing the number of transformers as well as you will be increasing the number of devices also for increasing number of pulses, but you may not be getting a much gain because the standard already says the 5% like. And then, so that is typically your isolated. Non-isolated, you can have a non-isolated transformer connection also for uniaxial full wave AC/DC converter. You may not find these connections in anywhere in the literature, not very popular, but in some application you may require, again we require star connection, zigzag T connection, or you may have a Scott connection. These are the 4 connections possible for getting these full wave to convert 3 phase supply into the number of phases 6, 12, 18, 24, which are multiple of the 6 or so. So, all these 4 pole connections, if you look into, this is non-isolated, means you do not have isolation, you are using auto connection of this, and you are converting 3 phase supply, which you are giving 3 phase here, which go directly to output, and remaining 3 phase you are generating with the help of this transformer connection of your T connection. And you can see all the 6 phases with respect to the neutral, where one point of the load is connected. All the vertices will be, the radius will be of this circle equal to the same, that is RMS voltage you are getting in the output corresponding to the neutral point, and 6 identical voltage with the 60° phase shift, 6 phase supply, and you are able from 3 phase to you are, even without isolation you are converting 3 phase supply into 6 phase supply, and you are using 6 pulse full wave converter here, and this is the 6 phase supply, how we convert 3 phase to 6 phase. And then similarly you can have with this connection your typically how you are designing it virtually this transformer, auto transformer connection with the phase shift and what kind of winding number of turns you can decide from this depending upon the input voltage, like that is the concept of the design. And we can call it T connection transformer for 6 pulse AC/DC converter is made of 2 single phase transformers, M and main and TZ transformer connection orthogonally on primary and provides the neutral point, and the transformer T has 4 windings connected vertically, while the transformer M has a 4 winding connected in horizontally, and the voltage of these windings in terms of the supply voltage can be determined as the VT1 will be of VA, that is the supply voltage RMS 1 minus cos theta, this will be half the voltage of VT1 VT2, and then VM1 will be your VA cos VA sin 60, and it will be a 0.8, or you can call it root 3 by 2 VLP, where VM2 equal to VM1, and the value of constant giving your winding voltage as fraction of the input voltage for 12 pulse, 18 pulse and 24 pulse converter configuration can be determined in the similar way, and these can be are found as, because for 12 pulse converter you require to convert 3 phase to 12 phase, and for 18 pulse you have to convert 3 phase to 18 phase, and for 20 pulse you have to convert 3 phase into 24 phase, and these are the 12 pulse converter, the constant which you require, which we have used in the winding configuration. Similarly, for 18 pulse these are the constant for which you require design of winding, and then 24 pulse these are the typical constant like, and you can just have a connection how look like for 12 pulse. Okay, you converting 3 phase supply with this T connection into 12 phase, and you are using 12 diodes, and you, with respect to neutral you will have a 12 phase voltage of equal magnitude which give you 12 phase supply. And similarly here this is the transformer how you are going to design with the phase shift, and these are the K1 K2 constant I was talking about in the previous equations. Simple geometrical relation which even the schooling mathematics is required for designing of these like also, but of course it is a circle not the elliptic, that you have to be cautious. And this is another connection we are using like a typically for converting this into 12 pulse. This is typically for 18 pulse, how you are getting 18 phases, and how you are getting the constant like these different constant to decide the number of turns. The solid line represents the set of 2 auto connected transformers which have several windings on typically on the transformer, auto connected transformer. They are not isolated winding, they have to be isolated so that you can make the connection, and 3 phase supply is converted into 18 phase, and you are able to have 18 diodes to have it 18 pulse converter, but the lowest harmonics here also will be 17 like. Similarly, you have a 24 pulse, this is the auto connection for 20 pulse converter, and 24 pulse converter you are converting 24 phase, and you must have a bit nearby consequent phase angle 360 by 24, that is 15 degree. So, 3 phase supply of without isolation with this auto connection we are converting into 3 phase supply into 24 phase supply, and we are able to have this 24 pulse converter. The lowest harmonics here again 24 plus minus will be there, so it will be 23rd and 25th, and certainly you will get the TAD much lesser than 5% on the input supply for this connection like, or this converter of 24 pulse like. And this is another connection of course of 30 pulse full wave. I mean you can design for any kind of, but these are the some of the innovative connections also. And coming to the results of 6 pulse, how it look like, you have a supply voltage and these are the different converters like, okay. I mean you can think about, and finally I mean you can find out this supply current A phase, B phase for 6 pulse, but you can see here because of the leakage reactance you will find I mean little notch in the voltage, but you will get the current may not be so straight. This effect the TAD in place of 30% it comes 25.44%, and that is the reason the harmonics are slightly reduced from 30 to 31 to 25% because of effect of leakage reactance like. I mean that effect of leakage reactance which does not allow sharp change of the current certainly reduces some of the harmonics. I mean it is forcing your wave to go towards a sinusoidal like. And coming to like a 12 pulse converter, you can see this current waveform. I mean of course it could have been a step wave, but because of leakage reactance you will find this waveform compared to 6 pulse is further going towards the sine wave. And of course because of this you have a little overlapping notch in the voltage, and the TAD here in place of 15% it reduces to 11.2% because of effect of leakage reactance. You can clearly see the waveform going closer to the sine wave now. Coming to like 18 pulse, you can see the waveform how it look like. I mean because of leakage almost looks like a continuous current and all 3 phases, and you can see even the TAD in place of typically order of like a 12%, it reduces to like almost 6.235% like, almost to half like because of effect of leakage reactance like. And when you go for 24 pulse, you can see the current very close to the sine wave, and the TAD is 4.8%, and which is well qualified IEEE 519 standard. By adjusting the leakage you can further reduce the TAD maybe order of less than 4.5 order of 4% in that case. So, these are the typical how really practically this your full wave even non-isolated category also, I mean you may get good performance, and this is the typical performance typically T connected for different number of 6 pulse with the load how TAD varies of the voltage and how TAD varies of the current typically like, I mean also and then for you can call it for for how the TAD varies for typically corresponding to of the current from starting from 6 pulse at full load, how it go to 4.8% from here to here, from 6 pulse to virtually going to be 24 pulse like in these full wave converters of T connected like. And then the TAD corresponding to like you can call it 24 pulse for blue, then 18 pulse, then your 12 pulse, and then 6 pulse. Certainly 18 and 24 may not have a much difference, that is the reason many applications we prefer to use the 18 pulse converter also like. Now coming to your multipulse AC/DC converter for unilateral power flow, I mean unilateral multipulse bridge AC/DC converter. I mean those were full wave, now we are talking about bridge. So, isolated unilateral multipulse bridge AC/DC converter, these are possible with different transformer connection, and you have a transformer connection like delta star, Scott connection, polygon connection, and many connection can be used here for example. So, this is typically 12 pulse converter. I mean you have a one typically directly taking another delta to star, and you get a typically your 0 to 30 degree phase shift, and you get a typically 12 pulse conversion. Here you again you are getting typically here I mean like pulse doubling. This is the pulse doubling circuit for converting 6 pulse into typically of your 12 pulse like, it is called pulse doubling. And similarly here we are using standard connection of your star delta to star to get a 30 degree phase shift between the two nearby, which normally use many applications like HVDC or otherwise, and we are able to connect here because of isolation. Either you can connect them in parallel or you can connect in series, but if you are connecting in series this interphase transformer is not required, but for parallel connection for equaling sharing the current in both we require this interphasing transformer. Or then this is another connection for getting a phase shift of your 0 to 30 degree using this T connection, that what we really discussed earlier, or Scott connection, and then this is another connection for getting pulse doubling here in this delta to star connection, then giving a pulse doubling. Of course, we require neutral point for this pulse doubling concept to 12 pulse. So, there are plenty of way that how we can realize this 12 pulse with the bridge configuration, 2 bridges are required. So, this is typically you can call it a short connected transformer. Two are using, one transformer is like a vertical, another is vertical, one is horizontal. So, all windings are on typically on two transformers like also. And this is another typically now 18 pulse. We are giving 0 and plus minus 20 degree phase shift for 3 converter, connecting them in series, and this gives you 18 pulse isolated category. Then this is again 24 pulse, in the sense you have a 6 to 12 pulse you are having plus minus 30 degree phase shift, and then you have pulse doubling with the help of this ripple injection. So, we have a 3 concept. By this all 3 concept we have looked into. One is the phase staggering or phase shift, another is the multi-phase, that is we converted multi-phases, and the third concept is your ripple injection or pulse multiplication we call it, or pulse doubling with the diode. But thister we can increase the multiple number of ripple injection, we can increase the number of pulses, even not necessarily double, 3 times 4 times also people are able to practically realize even in the research laboratories also. And that this is again with pulse doubling 12 pulse to 24 pulse, and this is really true 24 pulse with the 4 bridge, how we are connecting it and getting a phase shift from these 2 transformer with the extended delta, and we are able to get 24 pulse all bridge we are connecting, and 15 degree of course phase shift is required. Similarly, for T connection this is 24 4 pulse 4 bridges, and phase shift we are getting accordingly your plus minus like a 15 degree phase from 0 to 15, then 0 to 15 to 30 and 30 to 45. So, we are able to get phase shift, and these are the 2 transformer we are using in this connection, only like a kind of T connection. One is vertical, another is horizontal. So, we might be having several winding on the typically on 2 core of 2 transformer like. And now, we can say this non isolated multipulse auto connection based configuration, that is non isolated category. Earlier we use isolated carry, maybe star connection, delta connection, polygon connection, delta polygon connection, hexagon connection and T connection. And you can see zigzag connection. So, how many connections you have to connect the transformer? Typically 3 plus 3, 7 way you can connect the transformer, even auto connection mode to convert to give a provide the phase shift or to get multi-phase. And another classification, we can divide them into number of pulse phases like 9 phase or 15 phase. I mean 3 phase can be converted to 9 phase, or it can be converted to 15 phase, and this is something you can get a phase staggering. So, here so many connections are possible with the transformer and with the number of pulses. So, considering the realization of 12 pulse converter, first we have a conventional star delta transformer which require a large kVA rating and more cost and difficult to make identical star and delta winding, and this is typically you can call it the star connected auto transformer based configuration. With this 4 type of arrangement, I mean we have a star, it is a non isolated auto connection, we have to provide the phase shift between plus minus on both the side plus minus 15 degree, and all these points will be on the circle. So, that you get with respect to neutral you are getting equal voltage. So, you are converting, you are giving for a phase shift, you are getting 2 sets of 3 phase supply which are plus minus 30 degree phase shifted, and you are using 2 6 pulse converter with the interphase transformer here, and then able to get the DC of 12 pulse here, and TAD here of course will reduce because of 12 pulse, lowest harmonic will be 11. Then you can use any load like a maybe a variable frequency inverter based voltage source inverter based index motor drive or any other motor drive with, and this is the simple design like a geometrical design for schooling, that how much phase shift you have to provide it. I mean this is typically you can call it the input voltage. I mean you have a input voltage of this, in terms of that you can find out this is input voltage, and you have to get output voltage corresponding to dash with this of 2 phase shift. So, you are getting one this voltage and you are getting another this voltage with the 15 degree phase shift from the original voltage. These are original voltage and these are the constant which you are getting K1 K2 constant here like and you are able to get typically the TAD of this 12 pulse converter in place of 15 pulse. Because of the effect of leakage you are able to get typically order of only 9.89. Interesting is the magnetic rating is only 36% here, but this is also on higher side if we talk about some other connection like, and the TAD when we talk about light load of course it goes towards 15% which is, but at full load it reduces to less than 10% because of effect of leakage reactance like. Now, experimentally this was realized, and TAD experimental we observe at full load around 7%, at light load we observe around 10%, and that the reason the power factor of course here with that much TAD is order of displacement factor is unity, and here of course the displacement factor goes little around 0.96 or so. This is the another 12 pulse with extended, we call it like a delta connected 12 pulse. So, we are having extended delta to one we have it directly, another is plus 30%, which we are getting for second bridge, okay, and then 2 bridges same way, and this is the typical design how we are designing for providing the phase shift of typically of your 30° phase shift and getting K1, K2 constant and the output voltage. And then the performance of this again less than 10% of full load, and at light load we are getting around 15% out of that. That is the ideal case like. And there is another connection extended delta we call it, okay, and the what people have used it this 12 pulse, and then you use a small rating low rating pendulum current source to work as a active filter, and they are able to get the TAD here even order of 1 or 2% like with the help of that. Another is like to get pulse doubling with a zigzag ripple injection, this 6 pulse we are able to convert 12 pulse from this auxiliary transformer to capacitor additional one. And now for realizing the 18 pulse, I mean like we can have 18 pulse in many way. One way that we are giving a phase shift typically I mean plus minus 20°, and we are able to get 3 of course in auto connection we can connect them in parallel, but we require interphase transformer here. So, we are able to have 18 pulse converter, and this is the design. So, plus minus 20° we are getting from original. So, one is original, another is 24 pulse, but all should be on same circle to have equal RMS voltage like also. And these are the constant how we are getting these constant in the typically by calculation of geometrical calculation making this on the same circle. And then the performance of this you can say the TAD at full load for this 18 pulse comes only 2.72%, at light load it comes only 4. So, it qualifies IEEE 519, and that is the effect of how the leakage reactance affect your TAD here like. And here the of course magnetic rating for this is only 41% because of the you can call it auto connected, and this is the extended delta connection for 18 pulse again plus minus 20°, I mean plus 20. This is your you can call it the coming to original one because it is originally connected input, and this is your minus 20°. So, you are getting like a here 18 pulse with the phase staggering plus minus 20°, and here the design how we are going with the with this phase shift of corresponding to what we require here, and this is the constant what we really talk about K1, K2 here from geometrical relation of this nature, and we are able to get performance similarly like less than 5%, 4.17. Of course, light load is 5.56% TAD of this, but the magnetic rating for this auto connection is only 22.55%. The transformer rating is much smaller in this case like common also. Now, coming to this another configuration of 18 pulse can be realized by another way like 9 phase, but here the phase shift is your 40°. 9 phase means your 360 by 9. So, that require 40° phase shift. So, that is another way that you can have here 3 phase conversion into your I mean bridge configuration require your odd number of phases, that is either 3 or 9 or 15, and then you can have a bridges to convert into the odd number even number of pulses. So, 9 phase also will give 18 pulse. Another way was the phase is staggering plus minus 20, here plus minus 40°, you are still able to get like 18 pulse, but this is not preferred because for giving a 40° phase shift compared to plus minus 20°, you require more number of turns, and cost of the transformer and number of the turns in the transformer will increase, and kVA rating of the transformer will increase. That is the reason, but of course, practically it is possible to run like common also. And this is typically another one to get again 18 pulse to convert 3 phase into the 9 phase, and then using the 3 bridges corresponding to phase staggering corresponding to. So, here we are converting multi-phase, but 9 phase odd number of phases, so that we can convert 9 phase into 18 pulse with using the 6 again the 3 bridges. So, that is the multi-phase concept like, and how we are designing for this multi-phase typically I mean that is so for 24 pulse I mean this is again we require typically 4 converters, so 60 by 4 15°, and this is the way how we are getting 15°. This you can call it the star connected auto connected one, and then this is 24 pulse I mean, but we require interface transformer if we are connecting in parallel. We cannot connect in series because voltage level will be separate. So, for parallel connection it is possible to have auto connection these, and these are the really the constant which we require in all these, and these constant after calculating the phase shift how much we want from one to another, and that we are able to get K1, K2, K3, K4 in these auto connection like. And another concept was retrofit. Normally we are able to get little higher voltage as we increase the number of pulses, average voltage increases because ripple is reduced, but there was a concept of retrofit that you must get the same voltage. So, we have to reduce the output voltage or input voltage itself little lower around 4 to 5% as output voltage reduces. So, that output voltages are not affected, output DC is not affected, and you are able to use in the same application where you are using the 6 pulse converter. So, that is the concept of retrofit arrangement. So, you have to get little lower voltage what equivalent to earlier you are getting an output voltage by the same percentage. And by design you are able to get like in a 24 pulse converter TAD of 3.45% in place of 7.5%. This reduces to half, and this is the main reason is effect of leakage reactance of the transformer like. And here you are able to get in place again in place of 7.5% you are able to get 6.56 even under light load condition, that is 20% load on the converter like. And this is the typically you have to convert 3 phase to 9 phase for 18 pulse, and these are the how we are converting 9 phase with the 40° phase shift. If you look into here plus minus 49 and how you are getting the constant in the design, I mean these are the typically constant you are getting K1, K2 to get plus minus 40°. I told you this 9 phase is not preferred because giving a 40° phase shift you require more number of turns in the transformer and kVA rating of the transformer will increase compared to like your another phase staggering concept for your 18 pulse converter like. But of course, feasibility is possible, design is also possible, we develop also in the laboratory. So, this is 9 phase based 18 pulse converter. So, we convert 3 phase into 9 phase and then we give to this 9 phase 3 phase to one and 3 phase to another 3 phase to another to have 18 pulse converter by this method, but we of course, in parallel we require interphase like also. So, that is typically how you are connecting with the help of delta. And TAD comes in 18 to 3.79 and this is 7.35, but still it is less than your 7.5% TAD here like also. And this is the how we are designing typically this phase for phase shift for 15 phase. 15 phase means 360 by typically your 360 by 15. So, it will be like your typically 24° I mean from one to another, and with this fork connection you can get the phase shift your typically 24° plus minus with the help of this like as you can see here what is the original and what is the different degree like a 24° you are getting from this, and you are able to get typically the all you can call it like here 15 phase means your 30 pulse means you are just in 30 pulse you are using a 5 converter here which are connected in parallel with the here the 15 phase supply. So, each are getting this bridge is getting virtually from 3 phase, 15 phase means 5 bridges. So, you are able to again have to interface transformer, so that all are conducting, but if you are not doing interface only one bridge will conduct like. So, that also will distribute the current equally among all, and you are able to get in this 30 pulse 15 phase means 30 pulse you are, but rating is increasing 76% of magnetic rating in spite of your auto connection, and TAD of course, here you can see its order of typically order of 2.38% and order of 2.14 3.38 in case of current, and here you are able to get of course, well accepted TG as far as number of pulses 30 pulse are concerned. This is another way of course, you are having a 12 pulse with the fork base connection with the plus minus 15° and then interface transformer for 12, and how you are designing that is the method of designing to get the phase shift with this constant like, and then fork connection you can use for 24 pulse where you are having a phase staggering typically for 4 bridges phase 60 by 4 15°, and with the fork connection you are able to get like a this phase shift degree or typically a 15° from one bridge to another bridge, but you have to use interphase transformer like also. And then this is your typically again with the ripple injection you are having 12 I mean plus minus 15 means 30° phase shift, you are converting 12 pulse, then pulse doubling, with the help of that you are able to have 24 pulse here in the output like. And this is the how you are giving a phase shift with the help of fork connection, I mean over the star you are having for this auto connection typically for connecting the 4 bridges for 24 pulse converter, and these are of course the design equation with the phase shift and K1 K2 all constant you are able to get for this, all these constants are here calculated for providing these phase shift like from typically geometric relation like Of course, this is the MATLAB model was developed for already all connections and transformer model, and this is you can think about this 24 pulse how the supply current is there. I mean of course, it was for drive. So, this is supply current, supply voltage, supply current, and then the TAD of supply for this 24 pulse converter comes 3.22%, and this is typically from 6 pulse to how the TAD varies from current. I mean for 6 pulse 31 to 12 pulse comes to 8.98 because of effect of leakage, and then it reduces for 24 to at full load out of 3.22% like also. And this is for like a 24 and 12 and 24 pulse. I mean TAD you can see of light load, it is full load for 12 pulse, it is full load of 24 pulse, even much lower than half it reduces because of effect of leakage reactance like also. And of course 6 and 20, this is like a light load and full load comparison for the TAD for 6 pulse, then 12 pulse, and then your 24 pulse like, and how that your I mean the waveform and TAD for like a 12 pulse, and how 24 pulse the your current supply current is there, and how the TAD 3.2% 2% is there, and how the supply current look like for 24 pulse converter. And then of course the magnetic rating, you can just see the magnetic rating for 12 pulse is 20 this interface. So, this is the total magnetic rating for 12 pulse, but for 24 pulse it is 56.56. This is another reason why we are not further going higher number if standard is able to meet with the as far as TAD is concerned like this is we call it the your polygon connection for providing the phase shift. So, this is like a 24 with the polygon, 24 means 4 bridges. So, we have to provide the phase shift again plus like your typically 15 degree, and with the help of this we are able to get your 15 degree phase shift for 4 bridges connecting in parallel. This is interface transformer we are connecting, and this is the how the design is there for providing the phase shift on the same circle how we are getting with the phasor diagram, and how the equations are formed, and how we are getting these constants which are used here for getting the same voltage by simple calculation of arithmetics, and you are able to get the your typically TAD of the current here. Your light load and full load of this 24 pulse you are able to get typically 3.2% in place of your 7.5%, which is just half because of the effect of leakage reactance of the transformer also. Now, coming to multipulse AC/DC converter for bidirectional power flow. Bidirectional power flow means we are using the thyristor for the control converters, AC/DC converter for bidirectional power flow. So, it can be again full wave, bidirectional multipulse full wave, AC/DC converter, or and full wave is like you are using again you are converting for 12 pulse full wave 3 phase supply into 12 phase, and you are using in place of diode you are using the thyristors for controlling the output voltage. These are also used like I told you like electroplating application for very high current and low voltage application, where even only one thyristor is coming in path of the conduction. So, your losses are not increased like and this is another like 18 pulse 3 phase supply you are converting with these transformer connection into 18 phase, and you are using the thyristor converter of 18 phase which control the output voltage, but of course at the cost of reactive power burden on the supply side like also. And another is like typically 24 pulse. So, you are converting 3 phase supply into 24 phase supply, and then you are using thyristor converter for controlling full wave converter. Only one thyristor coming in the path of the current, and you are able to get 24 pulse in the output like, but you get a control of voltage, but at the cost of reactive power burden, but harmonics are certainly reduced at the corresponding to 24 pulse like. And this is again another connection of 12 pulse with the full wave, non-isolated category. Now, coming to bridge configuration of bidirectional multipulse AC/DC converter. This is like you can think about if we talk about isolated, we are converting 3 phase 2 sets of 3 phase 30 degree phase shift, and we are using like 2 converter to realize 12 pulse converter like, and then this is another connection of 12. You can connect secondary in the parallel or series, but you are providing the phase shift, and but if you are connecting in parallel you require interphase transformer. There are many connections as we have talked about in typically unidirectional power flows. In bidirectional power flow same transformer connections are possible, but you have to use the thyristor for getting a control of output power voltage, and you can have a bidirectional power flow as you can do in the thyristor converter like. So, similarly, here it is a kind of ripple reinjection circuit concept that you are able to do pulse multiplication like a pulse doubling with this circuit like in 6 pulse you are able to realize like 18 pulse here by increasing the number of pulses from 3 times from 12 to it is a 6 pulse converter, and by having pulse tripling 3 times you are able to get, and this is typically like a 24 pulse converter. You are converting like phase staggering 60/4. So, you are able to get like a 15 degree phase shift, as you can see here 15 degree plus minus 7.5, and you are able to convert with the extended identical you can call it the extended delta, and you are able to realize in series this 24 pulse converter like. This is another method of 36 pulse converter. So, we are having your delta to start 12 pulse converter, we are connecting parallel, but with this interface transformer and this 3 thyristor, we are able to convert 12 pulse into 36 pulse. So, we are having a, you can call it pulse multiplication concept in this case. We multiplied the, because of this circuit, we are able to multiply this 3 times, or even sometime we are able to do 4 times. So, this is 48 pulse converter, 12 pulse we are converting 48. So, this is another concept. One was the phase staggering, this we are using. Another concept have been multi-phase, which we discuss in probably 18 pulse and 30 pulse with the 15 degree, sorry, converting 3 phase into 9 phase and 3 phase into 15 phase, and this is another concept we are using here of pulse multiplication. So, 12 into 4. So, for these thyristor with the interface transformer, we are able to multiply the number of pulses output in the output around 4 times. So, it behave like a 48 pulse converter, and we are able to reduce the TAD on input side quite low in this control converter like. That is possible only in the thyristor. This is another configuration with 12 pulse. I mean with this, but here with the small kVA low rating pendulum bridge, we are able to reduce the TAD. I mean in 12 pulse it should be order of 15%, we are able to reduce less than around 1 or 2% in this case with the active interphase reactor. We call it this as a active interphase reactor, very small rating is required for that. So, those are the innovative concept people have used, and this is typically auto connection, means non isolated category. I mean plus minus 15 we are getting with this polygon connection, and then we are able to have 30 degree phase shift, and we have this typically 12 pulse configuration. Then or 3 phase we are able to have plus minus 20 degree, we are able to get now a phase shift of plus minus 20 degree for 3 converters, 60 by 3, that is a plus minus 20 degree, and we are able to get 18 pulse fully controlled converter like, I mean or so. Thank you.